What you're looking at is the complete life cycle of how a DRAM memory subsystem actually works. Not the protocol, not the chip itself, but the engineering that keeps memory reliable and fast across temperature swings, aging, and varying workloads. On the left, you have boot time training, a 15-step sequence that runs once in order during system bring up. This is what's happening during those long seconds between pressing the power button and seeing the BIOS screen. Each step builds on the previous one. You can't issue commands until the clock is trained. You can't train the data bus until commands work. You can't optimize equalization until the basic link is up. By the time you reach step 15, the controller has established a working contract with the DRAM, timings, voltages, equalization coefficients, all calibrated to the specific system at this specific moment. The reason all this exists is signal integrity. At DDR5 speeds, 6 gigatransfers per second and beyond, a single bit takes less than 200 picoseconds. The wires from the controller to the DRAM aren't long enough for the light to traverse in that time. Manufacturing variation, trace length, temperature, voltage, they all shift the timing of when a bit actually arrives at the receiver. Training is the process of finding the exact settings where data is sampled in the center of its valid window with maximum margin against drift. On the right, you have runtime maintenance. And this is the part most people don't realize exists. Memory training isn't a one and done event. The DRAM and the link drift continuously as temperature changes, as components age, as workloads stress the system in different ways. So the controller runs a dozen background tasks, each on its own cadence throughout the system's operating life. ZQ calibration runs every few hundred milliseconds just to keep impedance in spec. DFV recalibration compensates for slow channel drift. Read margin monitoring continuously watches the eye width and reports degradation before it becomes failure. ECC tracking counts correctable errors and feeds predictive failure analysis. That's how data centers catch dying DIMMs before they crash production. Thermal monitoring decides when to double the refresh rate. Row hammer accounting prevents security exploits. Each of these is invisible to software, but they are what keep memory working day after day, year after year. The bottom panels give context. The generation highlights show how training has grown over time. DDR3 introduced write leveling. DDR4 added VREF DQ training. DDR5 added a whole layer of features for row hammer protection, CRC, and runtime write training. Every generation, signal integrity gets harder and training flow gets richer to compensate. In the key components section, you can see the memory controller has three parts working together. The controller logic, the scheduler, and the PHY, which handles the analog signaling, and the DRAM itself. Wrapped around all of these are sensors, voltage, temperature, jitter, error counters that feed back into the maintenance loops. Modern memory subsystems are closed-loop control systems, not static pipes. And the example timeline at the bottom right makes the relationship between boot and runtime concrete. The 15 boot steps happen once, sequentially, at the top of the timeline. Then runtime takes over and you can see multiple maintenance threads running in parallel for the entire operational life of the system. The big takeaway is training at boot gets you started. Runtime tuning keeps you in the spec. The controller is never really done. It's continuously adapting. That's why a server can run for years with the same DIMMs and stay reliable even as the silicon ages and the conditions change. For a systems software developer, the practical limit is this. You don't program any of this directly, but it's the substrate everything you do depends on. The memory bandwidth you see, the latency you observe, the ECC errors that appear in your logs, all of it is the visible surface of the closed loop tuning happening underneath. Understanding that this exists is the first step to understanding why memory behavior varies the way it does, and why memory subsystems are one of the most carefully engineered, least visible parts of the modern hardware. Thank you.